So imagine that you have an object, and that object is divided into 3 different memory spaces. Now, somewhere in this object, you're going to store data, whatever it is that you're using the linked list for. Let's say this data is maybe a string, maybe it has also an integer, and perhaps it has a byte array of some images or something of that nature. Okay. So at this point, it just looks like a regular struct or a regular class or just any piece of information. What makes this unique is that we have 2 additional pointers here, this top square and the bottom square rectangle, that are pointers to other nodes. So let's say you have your second node on your linked list, and it also is divided into 3 memory spaces. And it has data. Maybe it has a string, an int, and a byte of different values than the first. You then can assign this piece of memory to be a pointer to the next linked list, the next node in your linked list, sorry. And you can define this piece of memory here to be a pointer to the previous node. Now, when I say it's a pointer to the previous node, we're not pointing from this square to this square. We're pointing from this memory space, this memory within this node, to this whole node here. So this is a pointer to this whole node. This is called a doubly linked list because you can traverse forward or backwards along the list based on having a link to the next node and a link to the previous node. Now, in this scenario here, you'll notice that I don't have anything yet defined as this because there is no node over here. So typically what we do there is we don't define anything, we just make that null. So this one here would be null. And then this, if there are no more elements in the array, would also be null. And if you're to add an element to the array, which you could do at any time, you would then create that next node. And we'll do that with code next. I just wanted to show you guys this way first. And again, you could have your data here, and it continues on. So a couple more things to note here that are interesting is in this picture here that what we've shown, the diagram on the left is considered our head node, and the diagram on the right is our tail, because you can't progress further to the top of the linked list from the head, and you'll know that by reaching this null here, and you can't progress further to the end once you've reached the end, obviously, and you know that by reaching actually this null here, because there's nowhere for it to go, but it does have it does of course have this one here. All right, let's see what this looks like in code now. So we'll go ahead and open our Visual Studio and create a new application. I'm just going to create a simple .NET Core console app. We're not going to give it any fancy names. So let's begin by creating a class. And my color scheme is black and white here, which is not necessary. It just makes it look a little strange, doesn't it? So let's call this node. That's kind of the the generic term for a piece of a linked list is a node. So in your class node, we'll make it public so it can be accessed externally. You're going to want to create a constructor. So let's do public node. And you're going to want properties in here that point to other nodes. So we can create those arrows like we had in our diagram. So let's do prop tab. It creates this for us, and we'll type in node. So we're creating it of the same type. Let's call this previous. And let's do the same for next. And let's give it some data as well. We'll create an integer property. We'll call it, I don't know, number of houses. Why not? And we'll do another. We'll make it a string. My favorite color. Or how about color of the day? Because you can't have too many favorite colors, and we're going to have a full-size list here, right? Okay. So if this is the first node being created, and at this point we may or may not know what the other nodes are, so let's just by default set previous and next to null. And let's create another constructor in case we do know what the previous or next is. And we'll say node previous node maybe that's it here, because we won't always be wanting to insert nodes outside of the chain. That would be kind of strange. So let's just insert it knowing what the parent is. In fact, parent is a bit more easy to understand than previous. So parent. So we could say node dot, in fact, let's rename this to parent as well. So we could say node dot, or this. Now this is a reference to this object that we're currently in. So this dot parent is equal to the parent that was passed in when we created it here. And I imagine that they'll probably know what they want when we first create it, but we could always add it later. So let's make them optional parameters. Number of houses. And if you assign it a value here, like I'm doing equals 0, it makes it an optional parameter. And let's do the same for color of the day. So if we don't know whether or not they're being specified, I think we should check for that to see if they have been specified. So let's say if number of houses, actually, I think we'll just, yes, let's do that. So if the number of houses is greater than 0, then we can assign our property to what came in as a parameter. And let's do the same for the other one. If color of the day is not red, and you know, colors is something you might want to use an enumeration for, so we could look into that as well. Set the color of the day equal to the local variable color of the day. All right, so we've constructed a really basic linked list here. I didn't choose byte like we had in our picture here. Just to make things simple, we just did a string and an integer for the data. But as far as the other two pieces, the parent and the next, those will correspond to the parent, oops, the parent up here, I'm sorry, the parent is this one, and the next is this one and this one, right? And this is our data, so this is our int inner string. So let's go ahead and see what that looks like from program here, from our entry point of our console application. Let's define a node. So we're using our class that we built called node, and let's call it my node, or whatever node you want to call it, house node, since we're talking about houses. And so my node equals new node, and you'll see we've got our two choices of parameter sets here. So let's just use the default one first to build the parent. Let's call it, I guess, the head of the linked list. And now we'll do node next node is equal to new node to build another. And this time let's use the other parameters. Let's make the parent be the head we just created. And let's give it a value for number of houses 6. And the color, we're going to choose blue. And now let's build next node. And we'll make it be the next item. And its parent will be next node. And we can give it 2. And let's not specify the last parameter. Let's let it be red by default. See how I did that there? It knows it's not going to use the constructor because it has at least one parameter. It's not going to use the default constructor. It has at least one parameter, but I'm not choosing that other optional parameter. You could do a for loop here and build a whole bunch of nodes at once, but it's also not necessary. So I'm going to put a breakpoint here just to show you what that looks like before we go further. All right, so we've hit our breakpoint. Now, if I hover over next node, you'll see that the parent of next node is this one. Oh, so first of all, next node has 2 houses. Oh, it didn't assign the color, so we'll have to take a look at that. But the parent of next node is blue. It has 6 houses, and its parent has no colors defined and no houses defined. So let's first change that. Perhaps in our we could give a default to the basic constructor as well. We could say, and we could put that default right here. It won't be in the parameters. So let's say number of houses, if we don't specify, is going to be -1. And color of the day, if we don't specify, is going to be green. Okay. All right, let's give that a run through. All right, so if now I hover over, actually let's put our breakpoint here so we can walk through it and you can see exactly what it's doing. So first time through, it's in the basic constructor, the default, and it's going to assign -1 and green to the first node. Next constructor, it's going to go in, and you can hover over these things to see what they are. You can see what the parent is. There's only one parent at this point. It's green, -1. Number of houses was passed as 6. Color of the day was passed as blue. So number of houses was greater than 0. It's assigning the one that was passed in 6. Color of the day is blue, so it's assigning that. All right, now we're going to go with our one that we weren't sure about that had 2 parameters. Stepping into it, parent is now blue, and it has a parent of green. Number of houses is 2. Color of the day is red, because we didn't specify, you see. So if number of houses is greater than 0, we assign 2. It did. Color of the day, red. Oh, it's not equal to red, so it skips this block with this if statement. So it never actually assigned it red. So we've just troubleshooted this and we know what to do now, right? Let's put an else statement here. Color of the day equal to, you could say either equal to this, or you could just directly say it's equal to red. We'll just say it's equal to this color of the day that's passed in with the underscore because we know that is red. So now it should be red. Okay, instead of walking through it again, we're going to make it a little more interesting, and we're going to go ahead and loop through it with a loop and show the output. But before we do that, we want to make sure we can traverse backwards and forwards. Now, going back to the diagram, we had two sets of arrows, going forward and going back. And when we created the elements in the class, you notice that we specified who the parent was, but we never specified the next node, or also known as the child node. So we specified these arrows on the bottom, but we did not specify these arrows on the top. So I think we should do that. That way we could start at the head and traverse to the end, printing out the results without recursion. So let's go ahead and do that. And I think the best way to do it would be in the node that we're passing in the parent to define the child, because we know that information at this point. So we could say the parent dot next is equal to this. And what's going on here is, because it's passing the entire object, including these two pointers here, it's passing the entire object by reference into here. We can reach into that object that was passed and change its properties. This statement right here will allow us to do that. So let's go back here and create our loop. Let's go ahead and tell it where we're going to start first, though. So we want to start with our searching node pointed to the head of the list. And actually, we can use a while loop for this. Let's say while our search node is actually pointed to a node. So we'll make it while it's not equal to null. And then we can traverse like so. Search node is equal to search node dot next. Now that next is defined. And since there's potentially data even in the head, we can put our outputs here as opposed to down here. So let's start with console.writeLine of search node dot number of houses, and we can make it kind of more descriptive. Number of houses is, and then apply 0 to be search node dot number of houses. And we can do the same for the color. Color of houses is my favorite color of the day. And let's make a description to say that we've moved to the next node as well. It's not really necessary, but next node. Some pretty printing here. Okay. What do you think? I think we need one more thing. We need to have a read line to have it stop. Oh, and you'll notice this is underlined here. We're missing a semicolon. There you go. So down here, let's do console.readLine to have it stop the input at this point. And I'll hit F5. There you go. So there's 3 nodes, starting with the head node where we didn't define houses, so I gave it -1 in green. And then the next node we got 6 in blue, and then we got 2 in red. Other things you might need to know with linked lists is perhaps how to move nodes around. how to delete a node. I'm not going to go too far into that. We could create a delete node method. Maybe let's do that. All you have to do for that is create a method in here. Let's put it below the constructor, public delete node, and let's have it take in a node as a parameter, node to delete. Sometimes when you give parameters a really descriptive name like that, it's really clear as to what needs to be supplied. And we probably want to make it return a node because we want to have the ability to delete the root node or the last node in the tree. So, sometimes if you delete a node out of the middle of the tree, you can switch those pointers around, saying the next node. Here, I'll show you with the picture. You could say the next node would, instead of being the middle node, would go all the way over. We'll basically skip that middleman. So if I was to show you with a pencil here, next would go here and previous would go here, and then we could get rid of these pointers, and then that effectively leaves no references left to the middle node. So you've cut it out of the list. That's the normal scenario, but you might also be deleting the head or the last element. So let's account for those as well, and we'll return the new root. That way, if you delete the first item, you know where to start from. So we could say if node to delete dot parent is equal to null, then we could just return, then we know it's the root, because only in a linked list with the structure we have it built, the only item that doesn't have a parent is the root. So then we could say, we could return, well, I mean, to make it correct as far as future traversals, we want to remove those links still before we return anything. So let's put a block out there. We're going to do multiple statements. We could say the node to delete dot next dot parent is equal to null, and we could say we could then return the node to delete dot next as the future root, and you'll want to notify that. Put the 3 dashes, press enter, and it'll kind of automatically drop this out. You could say deletes node and returns new root. So this would be returns is going to be the new root. You notice I haven't been doing this on the other methods, although I should have. Documentation is really important, but we've just been kind of covering as much ground as we can quickly instead. But that I wanted to show you that there. We know for deleting the root element, we need to supply the new root. If we're deleting a middle element, that's where we can supply both of those pointers. Let's cover that one last. Let's say if the node to delete dot next, or the child, doesn't exist, then it is the end of the list. This one might be best explained with the diagram. So if you have your next, and you have your previous pointer and your previous pointer, and we're removing this item here, there's no need to look over here to do anything because there's no pointers, and there's no need to do anything with this because we're removing this one. So what you would need to do is actually remove this, and then you can no longer get to this and it's effectively gone, right? So we could say node to delete dot parent dot next is equal to null. All right, so now all we've got left is our typical scenario where we're removing one from the middle. So from the middle, you want to set those the parent to skip it, and you want to set its child to have its parent be your parent. So we could go ahead and do that. So and we already covered these if statements here for those other cases. So let's talk about this one more time though. If you're at the end of the list, what are we going to return as far as the new root? I think the new root needs to be the root, which we have not specified. So in this case, maybe we should pass in the root. There are other ways of doing it. You could traverse here, but let's just say with our particular setup, we want to return the root. Make it easy. Just return the root as is, since we're not changing it. In this case, we changed it, right? All right, so let's go to that standard scenario we were just talking about. We don't even need an if statement because I think it's the only other scenario, unless we want to look at some extreme cases where we might be passed in null. But we could just put that in the requirements up here, must not be null, or something like that. So let's do node to delete dot next is equal to, so the node to delete dot next, so let's imagine that. So we're removing this item, right? So redefining this pointer would do us no value. We want to change this pointer to be this. So let's go back and take a look at that. Node to delete dot parent dot next is equal to node to delete dot next. Now what do we do with the other loop? Let's think about that. So we're removing this one. So removing this would do us no value because the node it's pointing from won't exist anymore. So let's look at its next values previous should point to its parent. So let's do node to delete dot next is equal to node to delete dot parent. Okay, let's go back to our program. The correct way of doing this would be to move this to a method to extract it. So let's just do that real quick. Quick actions and refactorings, extract method, and we'll call this method traverse and print. And let's give it a console write line. We are finished deleting, new results are. And let's traverse and print again. And just hit F5. Oh, there was a build error. Let's take a look at that. Oh, not all paths return a value. We did not return here. So we want to return the root because that's the, even though we've modified the list, we said that in our specification that we return the root. And have we called our delete? I don't believe we have. So let's call it after we've traversed it the first time to print the initial values. And let's call head equals to, and you can use any node because we did not make it a static. Oh, we did. We made it a static method. So let's do node dot delete node. And which one are we going to delete first? Let's try the head. And it says there's an error. Let's take a look what we're missing now. It says no argument corresponds to the required formal parameter of node. We didn't specify the root. The root is the head. All right, I'm going to just run right through it. All right, so before running the delete, we had -1 green, 6 blue, 2 red. Now we've got 6 blue, 2 red because we deleted the head node and made the new head to be the 6 blue. That's what we expected, right? So let's try our next scenario. Instead, we deleted the head first. Let's now try restoring it by stopping and playing again, and we will delete the middle element by choosing head.next to be our parameter of the node to delete. So let's see, that should have removed the blue. So we got green, blue, red. Now we've got green, red. We've removed blue. That worked excellent. All right, so now our last test, our last boundary case will be to delete head.next.next, which would be to delete the third one, but leave the other two intact. So green, blue, red, green, blue, red's been removed. So as you can see, those ones that we wanted to delete are no longer accessible, and we've succeeded. All right, that concludes my linked list demo. I think I fumbled around a little bit, but I showed you guys the concepts, and hope you liked it. Thanks for watching it all the way through to the end, and have a great day. Bye.